Hi, we're going to talk about chapter 5. And in chapter 5, you'll actually start learning about the elements and the trends in their behavior that creates the shape of the periodic table, essentially. So we're going to learn about electron structure. And so that will help us understand periodicity. So what are the periods in the periodic table? And the electronic structure of atoms is what really determines that periodicity. So one thing that's noticed is that you would think when you look at the periodic table that as elements get bigger, more and more electrons, more and more protons and neutrons, that there would just be an overall trend that they get bigger. But that's not what happens. What happens is they start out big. So when you think about, not sure there's a periodic table here. Done. They should have a periodic table in the slides here. Oh well, sorry. So look at your periodic table and realize that lithium, sodium, potassium, rubidium, cesium, and francium are all on the far left-hand side. And so what happens is you go across a period. Remember, period is a row from lithium to fluorine. The atoms get smaller, even though you're adding more electrons. And so the same thing is true across the period from sodium to chlorine, potassium to bromine. There are little glitches in there, which we can also understand by understanding the electron configuration, so the atomic structure. So this particular graph of atomic radius versus atomic number is kind of strange unless you understand something about the atomic structure. So in order to understand the structure of an atom and what the electrons look like, essentially, you have to understand electromagnetic radiation, because it's through the interaction of electromagnetic radiation, or light, with the electrons and atoms that we've learned everything we know about their electron configurations or their structure. And so we have to do a quick review of what is electromagnetic radiation. Some of you may have seen this in physics. Some of you may have seen it in chemistry. And if you've never seen it, we just need a little bit of an understanding. So electromagnetic radiation is characterized by its wavelength, its frequency, and its amplitude. So if you look at this picture, it's essentially a three-dimensional wave, but what it is it's a wave like is on the plane, so on this sheet of paper, that's an electric oscillating field. And anytime there's an electric oscillating field perpendicular to that, there'll be a magnetic oscillating field. That's not the important part of the field that interacts with atoms. The electrons are negatively charged particles. So this planar wave can just represent the electric oscillating field, because if the electric field is oscillating, it's going to be able to interact with negatively charged electrons. And so electromagnetic radiation is three-dimensional, but we only have to worry about one of the planes, the electric field. And so the wavelength, which is usually represented with a lambda, in pink here, that's the distance from one peak to another peak, so one complete wavelength. The frequency is if you were standing right there, so green frequency is nu, usually represented with nu. If you were standing right at that point on the wave and watching the light go past, it would be how many peaks that pass a given point per unit time. So the lights are the magnet or electric field is oscillating and moving, and so the frequency tells you how many peaks would pass you if you stood and watched it. The amplitude is just the height, so it's positive and negative. So the dashed line is 0. So you have a peak and a trough. So you have positive, negative, and the amplitude is from 0 up to the top of a peak. At the bottom, it's just giving some examples of different types so that you realize that the light or electromagnetic radiation that you're familiar with, something like ultraviolet that causes damage to your skin from the sun. It's a pretty high energy light wave, and it has a shorter wavelength. We'll see in a minute how energy is related to wavelength. Whereas something like infrared, which is heat radiation, that has a longer wavelength. And so the bottom picture is just showing you that the wavelength then characterizes what kind of light you have. And this is just a picture. It's also in your book, of course, that just shows you the difference in the wavelength and the frequency. So in a second, we're going to see the relationship between wavelength and frequency. And so we'll see that a long wavelength is a low frequency. And so something like gamma rays have a really high frequency, low, high frequency and small wavelength. And if you go to the other extreme on the energy side, radio waves, which you're bombarded with all the time, are going to have a super long wavelength and a super low frequency. And they've just expanded this little bit in the middle. That's the part, that small part that our eyes are sensitive to. So it's between ultraviolet and infrared, and those are the only wavelengths given in that expanded part there that's colored that your eyes can detect. So the energy from electromagnetic spectrum is going to have a relationship to the frequency or the wavelength. So we'll go through this. It's not on this slide. The wavelength times the frequency equals the speed of the light. So meters, if your wavelength is in meters and frequency is per second, 1/2, one whole cycle of light goes past every second. If you multiply those two, you get meters per second, and that's the speed of light. So C is defined to be the rate of travel of all electromagnetic energy in a vacuum, and it has a constant value. So the speed of light given here as C is 3 × 10⁸ meters per second. So it shows, if you look at the relationship, wavelength times frequency equals speed of light. If you have frequency or wavelength, they're related to each other. So when you look back here, there's a set wavelength that goes with each of the frequencies below. And so you can calculate the relationship. So the light blue glow given off by mercury street lamps has a frequency of 6.88 × 10⁻14 per second. And that unit of 1/2 is called a hertz. What's the wavelength? So all we have to do is plug it into the equation, and what will come out is, it would come out in meters, but we've added a conversion factor from meters to nanometers. So there are 10⁹ nanometers in a meter. So once we put that in, we end up with 436 nanometers is the wavelength of light that you see in a mercury street lamp. So when we're thinking about understanding atoms, we want to think about the time. So this was about 1900, and we didn't really understand atoms at all. And so we looked at experiments in chapter 2 and how they did experiments in order to understand that there's a heavy nucleus, very small, the electrons are around that. The nucleus has the protons and the neutrons, but they really didn't know much about what the electrons look like. So how do they exist around the nucleus? So one experiment that was being done at this time, and the experiment, a little bit before 1905, because I think it was in 1905 that Einstein got the Nobel Prize for explaining the photoelectric effect. So it says that if you irradiate a clean metal surface with light, it causes electrons to be ejected from the surface. So you move electrons off their locations on the atoms of the metal and they leave. So furthermore, the frequency of light used for the irradiation must be above some threshold value, which is different for every metal. So this shows you that in a graph. So shows you that you can be bombarding the surface with some frequency of light. So frequency is increasing on the x-axis, and the number of electrons ejected can be 0 till all of a sudden you hit some frequency where it goes straight up. Doesn't matter if the light's intense or not intense, so doesn't matter if it has a high amplitude or not. You're gonna hit a point where you start to eject electrons. And if it's lower intensity, you'll just eject fewer number, but that threshold frequency is always the same for a particular metal. And so from that, the photoelectric effect and Planck's postulate. So they postulated that when you think about light and you think about frequency, it's related to the energy of a packet of light. So this equation, which is Planck's postulate, says that the energy of a packet of light is equal to Planck's constant times the frequency. So that would make sense that as frequency goes up, the energy of a packet of light goes up, and so it's going to be able to remove an electron from a metal surface. And so this really is the relationship between the particle nature of light, which says the energy of the particle we call a photon for light is related to the frequency, which is the wave nature. So Planck's constant they figured out was equal to 6.626 times 10 to the minus 34 joules times second. So it's a very, very, very tiny number. And what this showed, really, the photoelectric effect, is that electromagnetic radiation is quantized. It comes in packets or particles. You can't split it into smaller packets of energy. And so Niels Bohr proposed in 1914 a model of the hydrogen atom as a nucleus with an electron circling around it. So now we're going to think about the theories that were being used to try to understand atoms. In the model, the energy levels of the orbits are quantized so that only certain specific orbits corresponding to certain specific energies for the electron are available. And so it's like thinking of Bohr's model, which has been found not to be correct, but it was the first model, essentially looks like this picture where you have the nucleus, that black dot in the middle, and then you have different places that the electron can orbit, different distances. And if the atom absorbs light, it can jump from one of those orbits to a higher energy orbit. And then also true, if it goes down in energy to a lower energy orbit, it can give off a photon of light. So this interaction of electromagnetic radiation with the electrons and atoms was teaching us a lot about the property of electrons. And so this is just showing what I was just saying. If electromagnetic radiation interacts with atoms, you can see different wavelengths of light that are absorbed. And this is just showing you that with a prism, or what really a rainbow is light that's perhaps white light, contains all the different wavelengths, can be split up so you can see the individual wavelengths. And so what happens is the experiments show at this time that atoms give off characteristic colors of light. So a line spectrum is a series of discrete lines on an otherwise dark background as a result of a light emitted by an excited atom. So in order to actually do this, I don't think they have a picture, you would have atoms and you'd make them into the gas phase, and then you'd pass electricity through them, which would give them energy, and their electrons would go up in energy, and then naturally they're going to fall back down in energy. And when they do that, they give off colored light, and they give off photons essentially. So in this case, it's showing you that the primary one for sodium is a yellow light. For neon, there's some blue, some green, some yellow, but they're characteristic lines. You don't get a continuous spectrum of just electrons giving off any old energy. They give off certain energies. And so at that time, they're trying to figure out what kind of theory could explain this. And so Balmer discovered a mathematical relationship for the 4 visible lines in the atomic line spectrum for hydrogen, and shows here that they're related to integers. So that n is an integer, and Rydberg's constant, so R infinity is a constant that you could figure out experimentally, but it really is saying that integers, so 1 over 2, an integer squared, minus 1 over some other n, gives you each of those 4 different lines. So n could be 3, 4, 5, and you'd get a different wavelength for each of those. So then Rydberg modified the equation to fit every line in the entire spectrum of hydrogen. And the difference here is that he replaced the 2 with an m, and we'll think about what that means. But that m is also an integer, just like the n is, and it's giving you the value of Rydberg's constant, which is also in your textbook. And so when we look at those lines, they're really the electron going from different orbitals to different orbitals. So you could start in 3 and go down to 4. You could start in 5 and go down to 2. And each of those would then be, m would be 5 and 2, and you'd get a different color of light. And so this, on the right-hand side, it's showing you that more in a different visual way, that you have the ground state where n equals 1, and then n equals 2, n equals 3, 4, and each of those lines represents a different set of m's and n's, which will give you a different wavelength of light with different energy. So m is the shell, the transition is 2, the inner shell, and n is the shell that the electron started in. And so when you do the calculation, you'll put n in for m, or you'll put in, do that again, the inner shell is m, so I guess the equation's here, I don't have to go back. So you'll put in the number, for example, the line on the very far left, the first one, it's going down to a 1, so m equals 1, and it starts out at 2, so n equals 2. And then you could look at each of those lines and decide what m and n are. So what they're noticing is that electrons don't behave the way that baseballs do. So electrons can't just have any old amount of energy, just like a baseball. Depending on how strong you are, you can throw it with a different amount of energy. What this is showing us with the Rydberg equation is that there are only certain energies allowed for electrons, and then their transitions can be understood by looking at how they interact with light, and then looking at that light to see what energy it has. And so in 1924, de Broglie suggested that if light can behave in some respects like matter, then perhaps matter can behave in some respects like light. So the photoelectric effect taught us that light, which we knew was an electromagnetic wave, had particle nature, and that the energy of one of those particles was equal to h nu in this equation. And so de Broglie thought, playing off that idea, if a wave can also be a particle, then maybe a particle can also be a wave. So in other words, perhaps matter is wave-like as well as particle-like. The de Broglie equation allows the calculation of a wavelength of an electron or of any particle or object that has a mass and a velocity. So the equation, and you'll do some problems with this, you can calculate the wavelength of any particle if you know its mass and velocity. And h, once again, is Planck's constant. So this is just an example of one of those calculations. So what's the de Broglie wavelength in meters of a car with a mass of 1,150 kilograms, traveling at a velocity of 24.6 meters per second. So you want to realize that Planck's constant, which has units of joules times seconds. If you look inside of a joule's real units are kilograms meters squared per second squared. So if you look at the numerator, if you take joules times seconds, you'd have kilograms meters squared per second squared times seconds. And so one of those seconds, numerator and denominator, would cancel. And so in the numerator, you end up with kilograms meters squared per second. So if you put the mass in kilograms, the speed in meters per second, everything's going to cancel and you'll get a wavelength in meters. And then you want to think about this. The wavelength of a particle is really a measure of the uncertainty in the location of that particle. So if you look at this, a car is a pretty big particle, and the uncertainty in finding it in a specific location is 10 to the minus 38 meters. That's insignificant. So a car doesn't act like a quantum particle. You can know where it is because its wavelength is so small relative to the size of the car. We'll see when we do the same calculation for small particles that that's not true. For electrons and atoms in general, you'll have a wavelength that's about the same as the size of the particle, which means the location of the particle is very blurred. So the wavelength essentially is telling you the uncertainty in the position of a particle. So in 1926, this is when quantum mechanics was finalized, Schrödinger proposed the quantum mechanical model of the atom, which focuses on the wave-like properties of the electron. And in 27, Heisenberg stated that it's impossible to know precisely where an electron is and what path it follows. And he called that statement the Heisenberg uncertainty principle. That's probably more familiar to you because there's a lot of jokes about it than Schrödinger's equation, but we model most of our math on Schrödinger's equation. You can also model it on Heisenberg's idea, but in general, that's done more in physics, not so much with atoms and molecules. So in order to solve the quantum mechanics of an atom, what you want to do is set up the wave equation. Set up the wave equation, which is a differential equation, and you are not expected to know calculus, so don't worry about it. But then you have to solve it. But the important thing is what comes out of that is something called a wave function, which is equivalent to what we call an orbital. So if you've had chemistry before, you remember s orbitals and p orbitals and d orbitals. Those are really solutions to Schrödinger's equation. And the important property that we'll be concerned with, the wave function tells us the probability of where you might find an electron. So the probability of finding an electron in the region of space is take that wave function and square it. So it shows you that right at the far right. So a wave function is characterized by three parameters called quantum numbers. And their quantum numbers are given labels n, l, and m sub l. If you have had calculus or differential equations, you'll realize that often solutions to differential equations have limitations and that there are quantum numbers or numbers that make the solution work when other ones don't. So n, l, and m sub l actually come from solving Schrödinger's equation. We're not going to look at that, but if you continue in chemistry or physics, you might take a class once you've had more calculus to understand really where these numbers come from. So the principal quantum number, so that n, describes the size and energy level of the orbit. It's commonly called a shell. It's going to be a positive integer starting with 1. As the value of n increases, the energy of the orbit increases, and the average distance of the electron from the nucleus increases. So we'll go through this. Then it's important to come back and connect everything we've talked about. So this might seem kind of abstract, but until we actually put it into action, you might not understand what questions you have. The angular momentum quantum number is L, and it really describes the shape of the orbital. The shape is generally called a subshell. So if you have a shell, for example, it might have L equals 0 and 1. And when L equals 1, that subshell is called the p orbitals. So we'll become very familiar with these ideas as we go on, but right now they're maybe a little abstract. There are n different shapes for orbitals. So if n equals 1, then L equals 0, and that's an s orbital. If n equals 2, you have more possibilities. L can be 0 or 1, and you have s's or p's. When n equals 3, L can be 0, 1, or 2, and you have s, p, and d. So at the bottom, it's showing you those. Those just come from historical ways that the shapes of the orbitals were discussed. So S is sharp, P is principal, D is diffuse, F is fundamental. So those are common names given to orbitals with different L values, just from an historical perspective. Magnetic quantum number, so the m sub L, it defines the spatial orientation of the orbital. And there are going to be 2 times L plus 1 values of m sub L, and they can have energy values from negative L to plus L. So if L equals 0, then m sub L equals 0, and there's only one orientation. But if L equals 1, then m sub L can be -1, 0, and 1, and it has 3 different orientations. So those are p orbitals. So when we look at those, we'll make sure we talk about the m sub L values. This is just a table that then puts the ideas for n, L, and m sub L into a table so you can be reminded of how you come up with them. And then this column right here, after the m sub L, is telling you if it has those values for n, L, and m sub L, what you'd call that orbital: a 1s, a 2s, a 2p. This tells you the number of orbitals in each subshell, and this is the number of orbitals in the whole shell. So in hydrogen, the ground state is a 1s orbital, and then the first excited state is either a 2s or a 2p. And just for the hydrogen atom, because it's unique, it only has 1 electron, everything that has the same n value, so the n value comes from looking out front the orbital notation. So a 1s orbital has an n of 1. A 2s or a 2p has an n of 2. So when you look at the far left and then the orbital notation, that helps you understand this diagram. So when you get to n equals 3, you have s, p, and d. And they all have the same energy. But when you add more electrons, they change the relative energies of a 2s and a 2p. So for hydrogen, they're the same. For anything else, the 2s is going to be lower than the 2p. And then the same thing is true for a 3s. Over here, 3s, 3p, 3d are the same. Over here, they go up in energy as the L value goes up. So identify the possible values for each of the 3 quantum numbers for a 4p orbital. So I said that the number out front tells you the n. So n has to be 4 for each of them. And a p orbital right here tells you L has to be 1. And so if L is 1 for a p orbital, that means each of the 3 that you're going to look at has to be a 4, 1. So n equals 4, L equals 1. But there are 3 different orientations for those, 3 different m sub L values. So you can have n equals 4, L equals 1, but you can have m sub L of -1, 0, or 1. It's really talking about how those orbitals are oriented in space. The shapes of the orbitals: an s orbital is spherically symmetric. You can have nodes, so you can have the white areas as you go out, kind of looks like a jawbreaker. There'll be a white area, and that's where there's 0 probability of finding an electron. So remember, the orbital is telling us where you might find the electron with the greatest probability. This is just talking about that node idea. So those white circles are regions where you can't find the electron at all. And it's really where the wave function went to 0. So if the wave function goes to 0 and the probability of finding the electron is the wave function squared, then 0 squared is 0, and you're going to have 0 probability at those surfaces, and you call them nodes. So these are p orbitals. The red and the blue lobes are just different signs. So if you have mathematically a plus function on one side and you go through 0, that nodal plane where there's a 0 probability, on the other side, then the function is going to be negative. So just like here where it's positive, goes through 0 and then goes negative, the pink says it's positive, the plane says it goes through 0, and then the blue on the other side says it's negative. These are just the 3 different orientations of those p orbitals. So a p orbital has 3 possible m sub l's, those 3 possible orientations. And so one can be on the x-axis, one can be on the y-axis, and one on the z-axis. This is a visual of what the d orbitals look like, more complex, but the same ideas. There are nodal planes where there's 0 probability. There are red and blue lobes where the function has a positive value and a negative value. And we are going to stop right there, and we'll do electron spin and the rest of the chapter in a second lecture.